All right. Good evening and good morning, everyone. I'm Jinfeng Zhao, researcher from Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, let me briefly introduce our valuable guest, Dr. Song Yang. Yang is a final year PhD student at Stanford University. His research interest is in deep generative models and their application to inverse problem solving and the AI safety. His first authored paper has been recognized with the Outstanding Paper Award at SAR 2021 and his oral presentation at Europe's 2019. He's a recipient of Apple PhD Fellowship in AI/ML and JP Morgan PhD Fellowship. Hi, Yang. You can get started with the talk. We sincerely welcome you.
Thank you for the introduction. Yeah, I'm very excited today to have this opportunity to share with you my research on deep genetic models. So in the past few years, we have witnessed a lot of progress in machine learning, and we have witnessed the enormous progress in applications such as autonomous driving, speech recognition, machine translation, recommendation systems, and so on. So in all those applications, we follow a single pipeline. Starting from the physical world, we first use human efforts to collect data, followed by data pre-processing and cleaning. This gives us a curated dataset. We then fit this dataset into machine learning algorithms to train models to perform a particular task. In this pipeline, data has become indispensable for the success of machine learning. For example, we need high-quality image datasets like ImageNet to train accurate models for image recognition, and we need high-quality text dataset like GLUE to train models that can perform multiple tasks in natural language understanding. And there are many other examples in other applications of machine learning. However, this data collection procedure is laborious in many cases, and what's worse, we have to repeat this process every time the setting changes or we have new restrictions. So the research problem in my PhD is, I hope to answer the question that, suppose we have enough data, can we use them to simulate this data generating process to create data under new settings? That is, can we produce a data simulator? So a data simulator can generate an unlimited number of data points. If this data simulator captured the essence of the data generating process, then we would be able to generate new data points under new settings. And similar to some simulators in other fields, we can also provide potential data points to this data simulator and query the probability values that those data points have been generated from the data simulator. So those data simulators have been studied with a long history in statistics and machine learning. In statistics, they are known as statistical models, and in machine learning, they are known as genetic models. From now on, I will call those data simulators as genetic models because I work in machine learning, and I will also use this symbol of a neural network to denote genetic models because I use deep neural networks to build genetic models. The question is, why do we need those genetic models? They have many different applications in the real world. First, suppose we have a genetic model on images. We may use it to convert stroke patterns to photorealistic images and share the semantics. And suppose we have a genetic model on patterns, we may use it to convert text to patterns that match this text description. And we can also use genetic models to help us solve challenging yield-post inverse problems, such as those in medical image reconstruction. Given a genetic model on medical images, we can use it to convert machine measurements of human bodies into high-quality medical images that are consistent with machine measurements. In computed tomography, for example, with genetic models, we can learn what a typical medical image looks like. And this can help us reduce the number of X-ray projections required for generating those CT images. And this is very helpful for reducing radiation. With the genetic model on traffic sign images, we can also use the probability values for outlier detection. For a typical traffic sign image, a good genetic model will assign higher probability. But for a suspicious traffic sign image, someone might have tampered with the traffic sign to cause confusion. And therefore, a good genetic model will assign lower probability to such images. And those probability values are very valuable information for our data distribution. And of course, generative models can be applied to other data modalities. This includes converting text to speech signals. And this also includes converting documentation into source code to boost the productivity of computer programmers. So generative models are so powerful. How can we build such generative models? It turns out that we can do this by estimating the underlying probability distribution of data. Suppose we have collected a large data set. As a toy example, let's suppose this data set contains many images of dogs. In statistics and machine learning, we typically assume that there is an unknown probability distribution called a data distribution that has generated every single image in our data set. Suppose we can find a probability distribution as our model to approximate this unknown data distribution. Then we can use this model distribution for many different applications. For example, we can generate an unlimited number of novel data points just by sampling from this model distribution. And because we have this model distribution, we can also compute probability values for any potential data point. For such an image, we can assign higher probability, but for an irrelevant image, such as this picture of muffin, we can assign lower probability. And because this model distribution gives us probability values and can generate an unlimited number of novel data points, it is actually a good generative model. The challenge of building those generative models is that our data distribution can be very complicated in for high-dimensional data like images or audio. And we need to find a very complex probability distribution model to fit our data distribution. So how can we find such a complex probability distribution as our model? Recall that in statistics, we typically work with simple distributions such as a Gaussian distribution. A Gaussian distribution is very simple. It is just a computational graph of 2 layers. Here, the first layer amounts to the input, and the second layer is the probability density function of this Gaussian distribution. So here, mu denotes the mean, and d denotes the dimensionality of x. But a Gaussian distribution is too simple. It won't be able to fit our complex data distributions. So we need a more complicated model distribution. And for this purpose, we need a bigger and deeper computational graph, and is a deep neural network. Now we hope to use a deep neural network to represent a probability distribution p theta. Here, theta denotes the weight in this deep neural network. And when we use deep neural networks to build generative models, we get deep generative models. However, it is non-trivial to use a deep neural network to directly represent a complex data distribution. This is because a deep neural network is just a function that maps a high-dimensional input to a typically one-dimensional output, which we denote as f theta. So the value of f theta does not directly represent a probability distribution because it might not even be positive everywhere. So to represent a distribution, we first take the exponential of f theta to make it non-negative, and then we can divide the output by a constant z theta in order to construct a model distribution that is properly defined. It is positive everywhere and is properly normalized. So here, the denominator z theta is known as the normalizing constant. It is given by computing the high-dimensional integral of this exponential function of f theta. For Gaussians, this normalizing constant has a closed form because Gaussians are too simple, and f theta in Gaussians has special functional form and allows us to compute this integral in closed form. But when we are using deep neural networks, this high-dimensional integral becomes intractable. And even in the simplified case where x is discrete and this high-dimensional integral becomes a summation, computing this normalizing constant is still sharply complete, which is at least as hard as NP complete. And this means computing this normalizing constant is a fundamental difficulty in deep generative modeling. Interestingly, this is also a fundamental difficulty in many other relevant fields, such as thermodynamics and statistical mechanics. So how do people in the current literature address this difficulty? There are mostly 3 approaches. The first approach is to approximate this normalizing constant with techniques such as variational inference or Markov chain Monte Carlo. Here are some examples. The cost is once we approximate this normalizing constant, we lose the ability to compute probability values accurately because those probability values require dividing by this approximate normalizing constant, which is undesirable. The second major approach is to use restricted neural network models, such that this normalizing constant is tractable by construction. So here are some examples. The cost is we have to use very restricted families of models, and this limits the flexibility of models we can build. The final approach is called Generative Adversarial Networks, or GANs. So GANs can completely bypass this intractable normalizing constant problem because they model the data generating process directly, not the probability distribution. However, because GANs are not probabilistic, they cannot compute probability values. So these are the three major challenges in current framework of deep generative modeling. If we are going to solve those challenges, what will be needed? First, we argue that we need very flexible models because this can address the second challenge and it helps us take the full advantage of the deep learning revolution, can use very flexible deep neural networks to build our deep generative models. The second desiderata means we hope to allow very accurate probability evaluation. So this addresses the rest challenges. This is very useful because probability values can be used for outlier detection, can be used for model comparison, and also according to the traditional information theory, we can use probability values for lossless compression. And finally, towards a better framework for deep generative modeling, we of course want to generate even better samples. We hope to produce new data points with better sample quality. We also want to control this sample generation process such that it can be used for solving challenging nilpost inverse problems, such as multiple image reconstruction we talked before. And in this presentation, I will show you one such framework that satisfies all three desiderata. The key of this framework is to work with score functions to represent probability distributions. So what are score functions? Suppose we have a continuous probability distribution known as the probability density function. We can define the score function as the gradient of log dx. So this is called the Stein score function or scores for brevity. So what does a score function look like? Here is a figure that shows the density function and the score function for a mixture Gaussian distribution. The density function is color-coded, where darker color means higher density. The score function is the vector field gradients and points to directions where the density function increases most quickly. So given the density function, we can compute the score function by taking derivatives. And conversely, we can compute the density function from score function by taking integrals. So mathematically, they represent the same amount of information. But computationally, I will show you that this score function can give us a lot of advantages. By working with this score function, we can build a new framework of generative modeling, which we term score-based generative modeling. And it satisfies all three desiderata. First, it allows flexible models because I will show you right after that this score function can completely bypass our intractable normalizing constant, which means we can use very flexible deep neural networks to model this score function. And we can also train those deep neural network models with principled statistical methods from data. The second point is by using score functions, we can generate even better sample quality than GANs. And we can also control this generation procedure in a more principled way for important applications. And finally, I will show you that even we only have a model for the score function, we can still compute probability values accurately with better empirical performance. And now I will first focus on how score-based generative modeling allows flexible models. Recall that previously the major difficulty is due to our intractable normalizing constant issue. Suppose we want to model this probability density function directly, then no matter how we change our model architecture or parameters, it always has to be normalized, meaning that the area below this curve has to be 1. Or in other words, the total probability has to be 1. And because of this, when we use a deep neural network to model this density function, we have to worry about this intractable normalizing constant issue. In contrast, if we model this distribution through its score function, then as the animation shows, there is no such normalization restriction in this score function representation. In particular, if we compute this score function for the deep neural network on the left-hand side, we can see that this score function is just the difference between two terms, where the only term that depends on this intractable normalizing constant is always 0, which says that the score function is the same as the gradient of this deep neural network, and this gradient can be computed with automatic differentiation. And I will denote this deep neural network model for our score function as theta, and I will call it a score model. So suppose we have collected a large training data set. Here, each point represents an image in our data set. We may use x1, x2 to xn to denote all those data points, and we can assume that the unknown data distribution is p data. With traditional statistical approaches, we can train a properly normalized statistical model p theta to approximate our unknown p data. And now the question is, can we do the same thing to train our score model to estimate the score function for this unknown data distribution? So this question can be formulated as below. We have a data set where each point was ID sampled from an unknown data distribution p data. Our goal is to estimate the score function of p data. We have a score model. This is a vector-valued neural network that maps the d-dimensional input to a d-dimensional output. We hope to train our score model to approximate our score function data. To achieve this goal, we need to minimize a training objective. This objective has to compare two vector fields of score functions. Here, one vector field is the ground truth score function data. The other is given by our score model. How can we compare their differences? Suppose we can overlap them with each other. We can compute the difference vectors between those pairs of vectors in those vector fields. And then we can average over the lengths of those difference vectors to form a single scalar objective. And this intuition can be captured by the feature divergence objective. So this feature divergence is just the expected squared Euclidean distance between the data score and the model score averaged over samples from the data distribution. However, this feature divergence cannot be directly computed because we don't know this ground truth score function of data. Luckily, there exists a famous method called score matching that can bypass this difficulty. It uses integration by parse to convert feature divergence into the following equivalent objective, which does not require us to know this ground truth data score function. The expectation in our score matching objective function can always be approximated using an empirical mean over our training data set. This score matching idea is quite smart, but it is rarely used in practice because it has a computational challenge. That is, we have to compute the trace of the Jacobian of our score models. And this trace of the Jacobian term is not scalable for high-dimensional data because when X has a lot of dimensions, its Jacobian will become a huge matrix, and computing the trace will require a lot of backpropagations. So how to address this issue? In our research, we rely on the idea of random projections. So suppose we have two high-dimensional vector fields which are close to each other. We can project them along random directions to get those randomly projected one-dimensional scalar fields. Those scalar fields will also be close to each other. So based on this intuition, we can effectively reduce the dimensionality of the problem to 1. And with this intuition, we propose the idea of a sliced score matching. So this is a computationally more efficient variant of score matching, where the cost of computing sliced score matching objectives is comparable to the cost of evaluating one single score network. In addition, we have also proved the consistency and asymptotic normality properties of a sliced score matching, meaning that this is a statistically principled approach. And due to time reason, I won't cover the detailed algorithm and proofs, but if you're interested, please read our paper. So here I have talked about how score-based genetic modeling may allow us to use very flexible models because score functions can bypass this intractable normalizing constant issue. And we can use principled statistical methods to train very flexible deep neural network models of score functions. For the next part, I will show you how we can generate new data samples by directly producing samples from our score models and how we can control this sampling procedure in a principled way. Suppose we have a large data set, we can always use score matching to train a flexible score model to estimate the score function of the unknown data distribution. The next step towards building a generative model is to find an approach to generate new data points from our score function. So how can we generate new data points from a given score function? Let's suppose this is the given vector field of a score function. If we have many random points in the space, can we move those random points to form samples from the score function? Well, here is one approach. We can move the points along the directions given by our score function, so that those points will have higher and higher probability values. But this won't be successful because all the points will collapse into each other. This issue can likely be addressed by injecting the right amount of Gaussian noise into the same procedure. So basically, we move points by following the noisy version of score functions. This is known as the long-term dynamic sampling approach, and it is also known to give us correct samples for any score function, as long as we keep this sampling procedure long enough until convergence and we set a sufficiently small step size. So now we know that score matching can estimate score function from data, and the long-term dynamics can produce new samples from a score function. So the most straightforward idea is to combine them together in order to generate new samples. This method works in principle, but does not work in practice. So here, the left figure shows some existing images in the CIFAR10 dataset. The right figure shows some newly generated images by combining score matching and the long-term dynamics naively. So clearly, there is something wrong with this approach. And in fact, long-term dynamics and score matching have been around for decades, but people were stuck on this problem of generating convincing images for almost 14 years. So what could be wrong here? We have identified several difficulties, and one challenge is the difficulty of estimating score functions accurately in low data density regions. So here is one example. We consider a mixture of Gaussian distribution. The left figure shows the density function. The middle figure shows the ground truth score function. The rightmost figure shows the estimated score functions. By comparing the middle and right figures, we can see that the estimated scores are accurate in those high data density regions, which are given by those green boxes. But in low data density regions, you can see that the estimated scores are not very accurate. So this is not unexpected because our score matching loss function only compares the difference between the data score and the model score averaged over samples from the data distribution. So for low data density regions, because there are almost no data samples, there won't be enough information to infer the ground truth score function from data. And because of this reason, long-term dynamics will have trouble exploring low data density regions when we are using the estimated score function from score matching. So how to address this difficulty? We propose to inject the right amount of Gaussian noise to perturb our training datasets. So after noise perturbation, our noisy data points will populate low data density regions to shrink the size of low data density regions. So this will help us estimate score functions in those low data density regions. So what does it mean to perturb our data points? Suppose our dataset contains many images, then perturbation means we inject Gaussian noise to each pixel of this image to make them noisy. In this toy example of a mixture of Gaussian distribution, you can see that the estimated scores are accurate almost everywhere after injecting the right amount of Gaussian noise. This says that by injecting Gaussian noise, those score functions of noisy data distributions could provide faithful directional information for long-term dynamics to move from low data density regions to high data density regions. The cost is once we inject Gaussian noise, those noisy densities are no longer good approximations to the original true data density. So how to address this issue? In our research, we propose to address this problem by using multiple noise levels to perturb our training datasets simultaneously. So as a toy example, let's suppose we have 3 noise levels from sigma 1 to sigma 3. We can use Gaussian noise of mean 0 and standard deviation ranging from sigma 1 to sigma 3 to perturb our training dataset. So this will give us 3 noisy training datasets. and we denote the underlying noisy data distribution as P sigma 1 to P sigma 3. So this perturbation process in the context of images will look like this. And after perturbing our training data set, our goal is to estimate the score function for all those noisy data distributions. The most naive approach is just to train a large number of separate score models to estimate the score function for each noise level. But clearly, this is not scalable because in practice, we might need thousands of noise levels, but we can't train thousands of score models separately. So in our research, we take a more scalable approach. That is, we train a single noise conditional score model. So this noise conditional score model is just a score model, but it takes the noise level sigma as one additional dimension of the input. The output of this conditional score model corresponds to the score function for the input noise level sigma. So how can we train this noise conditional score model? We leverage a mixture of score matching loss functions. So in this objective function, we have one single score matching loss for each noise level sigma I, and we have a positive weighting function to balance the scales of different score matching losses. So this helps optimization. The value of this positive weighting function can be given using principled theoretical analysis, or it can be given using empirical heuristic methods. So by minimizing this summation of score matching loss function, we are simultaneously minimizing each individual score matching loss function. And as a result, our noise conditional score model will be accurate for all noise levels. So after training, how do we generate new data samples? We first apply Lightweight dynamics to sample from the score function with the biggest noise level. The results will be used as initialization to sample from the next noise level. And we can continue in this fashion until we sample from the score function with the smallest noise level. So the sampling procedure is named annealed dynamics because the intuition is we gradually anneal down the temperature of our noisy data distribution for sample generation. And here is what happens when we apply this approach to several real image datasets. You can see that we start from very noisy initialization. We gradually modify the images according to our noise conditional score model, and this can give us high quality new data samples. The question is, how good are those samples? We can compare with the previous best approach, which was GANs. So GANs were known to be the best genetic model for generating new data samples, especially for images. As the Turing Award winner Yana Kun has said that GANs are the most interesting idea in the last 10 years in machine learning. And indeed, they have attracted a lot of attention and research efforts from big universities and corporations like Google, NVIDIA, and people have spent so much time on tuning GANs that GANs can really generate very astonishing image samples. But interestingly, with score-based techniques, we can actually outperform GANs on image generation on CFA10. And this is probably the first time that a different genetic model can outperform GANs on this task. And with better neural network architectures and better score matching techniques, we can further improve the sample quality on the CFA10 dataset. So here are some existing training images of CFA10, and here are some newly generated images from our score-based models. So this is a very challenging task, but you can see that our samples are quite realistic and diverse. Our samples are also different from existing images in the training dataset, meaning that you cannot generate such images by memorizing the dataset. Quantitatively, we compare with the previous best approach, which was a StyleGuide2 IDA. We achieved significantly lower FID scores and also higher inception scores. So this says that we can challenge the runtime dominance of GANs on image generation on CFA10 dataset. And our approach is also scalable enough to generate high quality, high resolution images. So here are two image samples from our score-based models. They have a resolution of 1024 by 1024. So they have millions of dimensions. And these are all additional images from the same score-based model with the same resolution. You can see that all those images look very realistic. Although they are not state of art yet, they are already quite comparable to the best GAN approaches on this task. Score-based models not only allow us to generate very high quality new data points, they can also allow us to control this generation process in a principled way. So suppose we have a generative model that can generate images of dogs and cats, but we only want to generate images of dogs. How can we do this? Suppose we are further given a forward model. So this is a model that gives us the image label Y for any given image X. In this case, it can be implemented with an image classifier. And we want to specify a control signal, here the tag label. We want to specify the tag label to be dog and generate images of dogs only. So this amounts to inverting our forward model to get this conditional distribution. And we call this conditional distribution an inverse distribution because it is a probabilistic inversion of our forward model. How can we get this inverse distribution? We can use the Bayes rule. So according to the Bayes rule, the inverse distribution is given by our prior distribution. This is the unconditional generative model at the beginning. It is also given by our forward model. This is an image classifier in this example. But we can't compute the normalizing constant in Bayes rule. So this normalizing constant is exactly the normalizing constant for our inverse distribution. But we know that this normalizing constant issue could be bypassed once we consider score functions. So here is the Bayes rule for score functions, which was derived by taking the derivative of logarithm functions on both sides of the Bayes rule. Clearly, this equation does not depend on our gradient of log py, because the gradient of log py with respect to x will always vanish. And as a result, this score function for our inverse distribution is just a summation of two terms, where the first term amounts to the unconditional score function, which can be given by training an unconditional score-based model. The second term is just the gradient of the logarithm of our forward model, which can be computed for image classifiers. In many other applications, it is actually possible to directly specify this forward model using our domain knowledge. So computing this derivative is also often very easy. The nice part about this decomposition is now we can plug in different forward models for exactly the same score model. Without retraining the same score model, we can use it for different applications. So here is one example. We can use score-based models to convert stroke paintings to photorealistic images. So here, the forward model gives us a stroke painting for any photorealistic image. It can be specified using a very coarse prior knowledge model. And with a score-based model trained on photorealistic images, we may use it to invert our forward model to convert our stroke paintings to realistic images. Here is another example. This is excellent work done by other researchers. So here, the forward model is an image conditioning neural networks and converts any image to text description. By training a score-based model on images only, we can use it to invert this forward model to generate images conditioned on text description. And here are some results. And this approach can also be useful for solving many medical image reconstruction problems. And for example, let's consider this computed tomography problem. In computed tomography, we use X-rays to project through human bodies. So those X-rays will hit a detector. This detector generates an observation called sinograms. If we can invert this procedure, then we can generate medical images that are consistent with our sinograms. And specifically, we want to consider the sparse view computed tomography problem, where our observation is sparse because we want to minimize the number of X-ray projections. Here, the forward model is given by our physical simulation because we can compute the sinogram for any given image using our physical knowledge. With a generative model trained on typical medical images, we know what a typical medical images look like. And we can use this generative model to invert our forward model to convert any sparse view sinogram into a high quality medical image. And here are some results on several realistic datasets. We only consider 23 X-ray projections, while in contrast, people typically need hundreds to thousands of X-ray projections in other approaches. So here is the result of a traditional compressed sensing approach. With only 23 projections, we can only get very blurry images. And here we use PSNR SSIM to quantify the performance of different algorithms. With deep learning approaches, we can directly map 23 X-ray projections into medical images, and here are their results. This is our result. This is a purely generative approach, and here is the ground truth. So from the numbers and from the qualitative performance, you can see that our approach can actually outperform other deep learning methods specifically designed for a particular number of X-ray projections. While in contrast, our algorithm is a purely generative approach, which means that we don't tell this algorithm what this task is about during training. And as a result, our method can be easily adapted to different measurement procedures and test time without retraining our models. And similar success has been observed on accelerated magnetic resonance imaging as well. And the research community has been quite excited about this progress in score-based genetic modeling, and people have reported many state-of-the-art results using score-based approaches on other tasks. This includes image generation on more challenging image dataset like the ImageNet dataset. So these are images generated from a score-based model. They have the better approach than even the best GAN algorithms. The similar success has been observed for audio synthesis, text-to-speech generation, material design, shape generation for 3D point clouds. And we have also observed the similar success for molecular conformation prediction and time series prediction as well. And some researchers from the University of Oxford have created a website called score-based genetic modeling.github.io, which includes a superset of those examples. And for now, I have talked about how score-based genetic modeling allows flexible models and how it creates higher quality new data samples with a more controllable generation procedure. And in the last part of the talk, I will describe how we can compute probability values accurately with better empirical performance. In order to compute probability values, we have to generalize the previous approach from using a finite number of noise levels to using an infinite number of noise levels. So here is a toy example. It is a data distribution made by a mix of two Gaussians. Suppose we have 3 noise levels. As an example, we can use Gaussian noise of mean 0 and standard deviation from sigma 1 to sigma 3 to perturb our one-dimensional data distribution. This will give us 3 noisy data distributions. We can use a one-dimensional heat map to represent each of those noisy distributions. With more noise levels, we have more heat maps, and in the limit of infinite noise levels, we will have a continuous 2-dimensional heat map. And here we use PT to represent each of those noisy data distributions, where T is somewhere between 0 and capital T. So T is a continuous parameter, and capital T is a fixed constant. When T is 0, P0 is the same as the data distribution because no noise is ended at this moment. When T is a capital T, P capital T typically contains a lot of Gaussian noise, and it will be close to a simple Gaussian distribution, which we denote as pi x. So given an infinite number of noise levels, how do we generate those noisy data sets? We leverage the idea of stochastic processes. Starting from the original clean data set, we can progressively inject Gaussian noise to perturb data points. The trajectories of those noisy data points will form trajectories of stochastic processes. By the end of this perturbation process, we obtain samples from the noisy data distribution P capital T, which are close to samples from a Gaussian distribution pi x. The so-called stochastic process is basically a collection of an infinite number of random variables. And here, each random variable is indexed by a continuous parameter T. For each random variable, there will be a corresponding probability density function, which we denote as PT. So a stochastic process will correspond to an infinite number of probability density functions. So by specifying the right stochastic process, we can represent our infinite number of noisy data distributions as well. We determine this stochastic process by solving a stochastic differential equation. So an SDE is typically have the following form. So here, Ft denotes the deterministic drift term, and dWt denotes the infinitesimal Gaussian noise, and Wt is the Brownian motion. So without loss of generality, we consider the following toy SDE, just for illustration purpose. But our method can be applied to more general forms of stochastic differential equations. So now let's consider how can we generate new data points using our SDE formulation. Because after noise perturbation, we obtain samples from very noisy distributions. So when sampling, we can start from the reverse process. We can first start by sampling from a Gaussian distribution. Those samples will be close to our noisy data distributions. And then we can gradually trace back the stochastic process in the reverse direction of time. This can gradually remove noise from our initialization and create high quality image samples. For any forward SDE of this form, we can show that the reverse SDE can be given in a mathematical form in below. And this reverse SDE relies on DWT bar. So this is infinitesimal noise, but in the reverse time direction. It also depends on our score function. So suppose we can estimate our score function. This will need us to have a time conditional score model. You can view this time conditional score model as a continuous time generalization to our noise conditional score model introduced before. And we hope to train this time conditional score model to approximate our score function of the noisy data distribution. And again, we can train our time conditional score model using score matching techniques. We have one score matching loss function for each time step t, and we have the same positive weighting function to balance the scales of different score matching loss functions. And by minimizing this training objective function, we can train a time conditional score model to approximate our score functions required in the reverse SDE. And we can plug in this conditional score model into our reverse SDE and then use any numerical SDE solver to generate samples by solving our reverse time stochastic differential equation. And this approach generalizes our noise conditional score model from using a finite number of noise levels to using an infinite number of noise levels. It also unifies diffusion probabilistic models into the framework of score-based genetic models. So now we know that by choosing an appropriate stochastic differential equation, we can perturb any data distribution into a single Gaussian distribution. It turns out that we can do this using an ordinary differential equation as well. And this is critical for computing the probability values accurately. The trajectories of SDEs and ODEs look qualitatively different, but they all correspond to the same set of marginal distributions as given by the background given by the heat map in the background. And in other words, they all correspond to the same set of noisy data distributions. For any SDE of this form, it turns out that we can get the ordinary differential equation using the following formula. So in this ODE, it depends on the score function again. And the score function can be approximated by training a time conditional score-based model. So after plugging our time conditional score model to the ordinary differential equation, we can determine the form of our ordinary differential equation. And starting from samples from the Gaussian distribution, we can solve our ODEs backwards in time, just like how we solved our reverse SDE. And this can convert our initial Gaussian vectors into high quality samples from our model distribution. And I will call this model distribution P theta. The value of P theta can be computed accurately using the following formula. So this formula connects the log P theta on any given data point x0 to log Gaussian distribution and a one-dimensional integral that involves the trace of the Jacobian of the score-based model. This trace term can be computed in polynomial time, but if we want faster computation, we can always form unbiased estimators of this term. And just like what we did in our slashed score matching technique. And this integral is a one-dimensional integral that can be computed with ordinary differential equation solvers. With this approach, we can compute probability values very accurately on several real image datasets. We report results in negative log probability, which is better when lower. And we report results in the unit of bits per dimension, meaning that what's the average number of bits needed for compressing each dimension of our data point if we use this probability distribution as a compressor. So here are some results on 2 image datasets. Those are our previous results. On both CIFAR10 and ImageNet, you can see that we achieve a lower bits per dimension than 8 bits per dimension. So 8 bits per dimension will be the number for images if we don't, without any compression. So this says that our probability models can actually have the potential for compressing images. And here is the result of our score-based models. You can see that we achieved the 2.38 on CIFAR10 dataset, which is quite close to the previous state of the art. We also achieved the new state of the art 3.76 on the ImageNet dataset. And it says that score-based models can not only challenge the long-term dominance of sample generation for GANs, but can also challenge the long-term dominance of autoregressive models and VAEs, and many other generative models on achieving higher probability values on test dataset. So as a summary, I will show you score-based generative models is they constitute a new framework for deep genetic modeling. They satisfy 3 desiderata. They allow very flexible models. They can generate higher quality new data samples with a controllable generation procedure for important applications in inverse problem solving. And they can also give us accurate probability evaluations. So that's it. With that, I'd like to thank you for being here. And I'm happy to take any questions.
Thank you for Yang's great talk. There's a question in the chat box. Can you look at it?
So one question is, what are the main breakthroughs to beat GAN? What was GAN missing, but you make it? So I think one biggest advantage compared to GANs is we don't have adversarial training. So our optimization procedure is very simple. We just need to minimize a given objective function. So the optimization is much more stable. The tuning is much simpler. So I think this is one reason why we can outperform GANs in image generation. The other reason is we have better connection to maximum likelihood training. And because of this connection, our samples can actually have better diversity. So usually we generate samples with much better diversity compared to GANs. And I also think that compared to GANs, we have some additional advantage like the ability to compute probability values accurately. And this is missing in GAN approaches. So yeah, so I hope this answers your question.
Yeah, the more questions coming up.
Another question is, I'm curious if you have explored whether the latent space learned in your last part of the talk has any meaningful interpretable dimensions. So this is also a good question. The answer is they don't have very easily interpretable dimensions. So it's very similar to normalizing fluid models. The latent dimension, the latent space has the same dimensionality as the input space. But unlike GANs or VAEs, those dimensions are not disentangled. So you cannot easily manipulate them for image editing. But still, you can manipulate the latent code for some applications like image interpolation or temperature scaling.
Yeah, basically, I have a question following the Stochastic one. You mentioned that your method, a generative model, can output the diverse image. Why this happened for outputting the diverse image compared more diversity than GANs?
Yeah, so I think the intuition is our approach actually has better connection to maximum likelihood training. In fact, if you change the weighting function lambda in our score matching loss function to a particular function, then our training can be viewed as maximum likelihood. So maximum likelihood estimation is known to generate diverse images, because if the images are not diverse, if we miss some modes in the data distribution, then our likelihood will be very bad. So it will put a very strong penalty to our loss function. So that's why with better connection to maximum likelihood training, we can generate more diverse images.
I see. I'm just wondering, would the GAN could be easily modified to maximize the likelihood, like you said it, to also increase its diversity as well?
Yeah, so it is possible. So there is a formulation that converts the loss function of GAN to like minimizing tail divergence, which is equivalent to maximum likelihood estimation. But because so GANs require adversarial training, so this connection is looser. So when you are trying to optimize the training objective, you do not have the guarantee that the tail divergence will become smaller. But here in our case, the score-matching loss function is actually a lower bound to likelihood. So if you minimize it, it's actually an alpha bound to negative log likelihood. So if you minimize it, our negative log likelihood will become smaller, and equivalently, the likelihood will become higher. So it has a better connection here.
I see. I understand. Thank you very much.
Hi, can I ask a question?
Sure, of course.
Hi. Thanks for your great talk. And I want to ask a question about like if the score-based generative model can like resist with some noise images or like outlier images, because when we're training a generative model, we have a lot of data, right? And sometimes we will make data like with some like erased area, or have the data with or have some outlier data in our training side. So how's this gradient-based method be affected by this noisy things?
Yeah, so if you have noises in your training data set, then you will expect that in some of our samples, we also have those noise. So some of our samples will have the same noise pattern. That is possible. Because the goal of generative models is to replicate the data distribution. If the data distribution is not perfect, then the samples won't be perfect.
Yeah, but I mean, if we made some outliers, so I don't know how like the performance might be dropped if we compare to the real distributions, right? So how the performance will drop if we add like more outliers in our training data. So I don't know what is the sensitivity of the generative models to this kind of noise.
So that really depends on how you define the true data distribution, because you mentioned there are outliers in your training data set. So are those outliers sampled from the true data distribution, or are they generated by other like distributions? So if they are generated from the original true data distribution, then you basically want to replicate those outliers in your samples. But if they are generated from a different distribution, then obviously the loss will suffer a little bit, and the performance will become worse. So personally, I haven't tested those cases. I think it might be something interesting to study in the future.
Okay. Yeah, and another question I want it's like more a general question about that, because nowadays privacy concerns have raised for many reasons. So how do you think about sometimes generative model may leak the privacy images like the human faces like that? So how do you have any opinion to the privacy concerns and the generative models?
Yeah, it is totally possible to leak some sensitive information in the training data set. So there are some recent work that try to address those kind of challenges. And one common approach is to leverage techniques in differential privacy. So basically, when you are training a genetic model, you can inject the right amount of noise to your gradients to make sure that you do not memorize any given specific data point in the data set. So this inevitably hurt the performance, but they will have better guarantees regarding like information leakage. And I think, well, in the future, if you can improve this further to the degree of generating very realistic images, then it can be very useful for privacy protection, because now you can train a genetic model on a given training data set and then synthesize another data set. You can release this newly synthesized data set to the public to avoid like harming those protected information in the original training data set. But still, we need to make sure the genetic model does not memorize sensitive information, and this requires progress in differential privacy or even better techniques.
Okay. I have a last question about some theoretical analysis. Because in your method, we can see your method can achieve the sometimes much better performance than previous methods, right? So it may mean like you only need the less training data to generate to estimate the density functions, right? So are there any like the theoretical analysis about like the score-based methods and the GANs methods about this rate? Yeah. Obviously, from your experiment, you have the better rates, right?
I haven't tried the case of having less data. So in all my experiments, I use the same number of data points for all like algorithms. So yeah, I'm not sure if we use fewer data points, what will happen.
I mean, you use the same number of data and achieve better performance. So you may have the better rate, higher rate than the previous methods. Yeah.
It could be that GANs are underfitting. Who knows? The genetic models are very different from classification tasks. It's easy to underfit, and overfit is actually not very easy.
Okay. Yeah. Thank you for your great work.
Yeah.
Okay.
Thank you. There are also another question in the chat box from Joker as well.
So connects the score function with the probability density function. So it's relatively easier to develop this SDE formulation because so first we want to increase the number of noise levels because empirically we found that using more noise levels can give us better performance. So it's quite straightforward to think about having infinite noise levels, and that will lead to stochastic differential equations. And another thing is diffusion probabilistic models are very relevant family of genetic models as well. And from the perspective of diffusion probabilistic models, they are basically discretizations of SDEs. So from that connection, it's also easy to think about SDEs. So the challenging part is how we get an ODE from the SDE. So that's because I was trying to investigate different ways of sampling from a stochastic differential equation. And in the literature of stochastic analysis, there are some existing work that tries to address this issue. And some of them uses like probability flow techniques, which are basically ordinary differential equations. So that's why I found out that we can convert the SDE to the ODE. And with ODE, you know, there are existing work called neural ODEs. And people in the neural ODE paper have discovered that we can view neural ODEs as continuous normalizing flows, which means we can compute probability density functions accurately. And that's why we can also do the same thing for score-based models through this ODE and SDE connections. Yeah, I hope this answers your question.
Yes, this is a very nice answer to my question. However, my question also wants to know that the score function that you mentioned in the first part of your talk. So how do you come up with this connection, the score function idea?
Oh, the score function idea is actually an old idea. So I mentioned the idea of a score matching. The score matching was originally proposed to train energy-based models. And for energy-based models, if you consider the score function, then it does not depend on the normalizing constant. So score matching was proposed to avoid dealing with this intractable normalizing constant for energy-based models. So basically, my research started from training energy-based models, and I encountered score matching, and I hope to make score matching work for deep neural networks for high-dimensional and large-scale data sets. And that's what happened. And even before score matching, people in statistics can be using the score function for many important things like proving the central limit theorem. And Charles Stein at Stanford, he's a famous statistician. He developed a technique called Stein's trick, and this is basically maybe one of the first papers that use the score function for applications. Yeah, so this is actually an old idea in statistics.
I see. Thank you so much. For one question, you have 2 answers.
Thank you for Yang's great talk. Boy Wang is assistant professor in the Department of Computer Science at the University of Western Ontario and affiliate faculty members in the Vector Institute. He also holds an adjunct position in the Department of Statistical and Actuarial Science, the School of Biomedical Engineering, and the Brain and Mind Institute at Western. His research interest involves all aspects of machine learning, theory, algorithm, and application. He received his PhD in computer science from McGill University before joining Western in 2019. He was a postdoctoral fellow at the University of Pennsylvania and Princeton University. Hi, Prof. Wang. You can get started your talk.
Hello, everyone. I'm Boy Wang from the Department of Computer Science, University of Western Ontario at Canada. So today I'm going to talk about trustworthy machine learning. In particular, I will talk about the 3 pieces of our recent work on robustness and fairness. So we all know that machine learning techniques have advanced significantly during the past 2 decades. So I talked to many people in different fields like computer vision, biomedical engineering, finance, software engineering. So they are all interested in machine learning. So what is machine learning? From my aspects, machine learning is techniques that build a computer system that acts like a human being by learning from data. So in other words, in order to make all this application works, we need to fit data, a huge amount of data, into a machine learning system. So we're all seeing this eye-catching success stories in deep learning, like how the neural networks can achieve or outperform human-level performance on game planning and computer vision tasks. But all these success stories are accompanied with big data. However, when it comes to data, we have several particular issues. So first, we may have a data shift problem. For example, when we design a self-driving car system, we may build this same system in a like simulated environments, or in one city. But later, we may use this system in like a real world or like in another city. So in this scenarios, we may have this what we call the distribution shift problem. So we want to build a reliable model that's robust to such a shift. Another example is from the medical applications, like this one. This is what I did when I was a postdoc at Princeton, where we collected the brain signals from different subjects during sleep. It turns out collecting this data is relatively simple, but annotating this data can be very expensive, especially annotating like the data with higher quality labels. It is very hard. It requires expert knowledge, basically. So we have this also have this label noise issue. So in both cases, we want to build a robust machine learning model to handle either data shift or label noise. So this is one issue. Some other issue when we build a trustworthy machine learning model includes in some data collection process, the data sets are biased, or the data sets are imbalanced in nature, right? We have a minority group and also majority group. So consequently, a machine learning algorithm may treat some groups of a population in an unfavorable way. Okay. So this is the fairness issue of machine learning. Some other issues include the black box issue, right? We only the deep learning model only give us the output without telling us what happens inside. And also when we train the models using big data, we also have this privacy issue. So those problems basically tell us we cannot just aim to build an accurate machine learning model, but also a trustworthy machine learning model. So what is a trustworthy machine learning? And there are many attributes to a trustworthy. So here I just list some of them. Okay, robustness, fairness, privacy, explainability. So those are the, I think, most active topics in the trustworthy machine learning. And in this talk, I will mainly focus on the first two, the robustness and fairness. Okay, the first one is robustness. In particular, our first work focus on the robustness to the distribution shift problem, which is also referred to as a domain generalization problem in the literature. So what is domain generalization? So basically, a domain generalization aims to extract the knowledge from multiple observer domains. Okay? That is robust to unseen but related to related domains, and which is called target domain. All right, so we have several data sets, and we build a reliable model, robust model, and we hope that this model can also generate to another data set from a slightly different distribution. So that's the overall objective of domain generalization. And one common approach to domain generalization is learning a domain invariant feature representation. And the high-level motivation of such approach is that if features are invariant to the source domain shift, they should also be robust to any unseen target domain shift. That's the high-level idea. So we use this source domains to extract the robust feature representation, and we hope that this representation is also robust to unseen target domain. So in order to do so, we have to consider both the empirical risk minimization and also the domain environments. So we have this overall objective function, which is adopted in most existing domain generalization approaches. So the first term is empirical laws on the source domain, and the second term is the domain environments regularization. Okay. So here phi is a representation to extract this robust features, and H is a classifier built on the top of this representation that is shared across the domains and also applied to the target domain. So when we align different domains, usually there are three types of environments. The first one is marginal environments, where we only align the marginal distributions in the feature representation space of phi x. Okay. Of course, this alignment has some serious limitations because it doesn't take into the label information into account. Okay. To address this issue, people start to study the conditional alignments. In particular, we can study either what we call the feature conditional environments, which align the px given y, or the label conditional environments, which align py given x. In both cases, we capture the label information into the domain alignment. Okay. Okay. So in this work, we reviewed that only considering these two criteria is still not enough. Okay. even though we use conditional alignments, it is still not enough. Okay. More specifically, we theoretically show that actually sufficient conditions for a successful domain generalization methods. And this in our theoretical analysis, we build an upper bound on the target domain, which involves 3 terms. Okay, and the two of them are corresponding to the risk, source risk, and also the environment's alignments. But we also, our theoretical results also reveal a 3rd term, which is missing in the current literature. And based on our theoretical insights, we also propose an efficient regularization term. And we show that with this very simple regularization, we can actually get a sufficient improvement. All right, so first let's look closer at the limitation of the current alignment methods. The first one is marginal alignment. So here, consider we have 2 domains, source and the target. And let's say we assume that they are all the same. The only difference is they have different prior distribution, right? And then what we can do is we just follow standard marginal alignment procedure, learn an embedding function phi and a classifier h, such that the marginal distribution are perfectly aligned and the source domain risk is 0. And then we can show that actually it's very obvious that such model, even though achieve 0 error on the source domain, will only achieve the accuracy at most 0.2 in the target domain because of the label shift problem. Right. Another example is we can just flip the sign of the decision boundary for binary classification problem. And in this case, again, source and target have the same marginal distribution, but since the sign is totally flipped, then the accuracy will be just 0. Okay. So in both cases, it is obvious that only aligning marginal distribution is not enough. Okay. Okay. So the next thing is how about learning the conditional environments? Okay. Well, learning conditional environments kind of address those aforementioned issues, but still it has its own problem, which is called overmatched representation. It happens when the probability distributions of the source domains are too complicated, or they are very similar to each other. And if in this case, if we just align the source domains by brute force, then a small perturbation in the target domain will incur a large change in the decision boundary. So this is something like an overfitting problem, right? So now the question is, how can we address this overmatching problem? Similarly, we add another regularization term to control this model complexity, which we call model selection. Okay, and this is the main theoretical founding of this work. All right, so everything for now is very straightforward and intuitive. Okay, our task is how can we formalize such intuition into mathematical equations. Okay, so in order to do so, first we introduce some preliminaries. Okay, the first one is the embedding. Okay, we treat the embedding as a conditional distribution. Okay, given the input x, the embedding will just the conditional probability of z given x. Okay, so this phi can be viewed as a conditional embedding, conditional distribution. And given this definition, we can define the marginal and the conditional distributions over the representation space. And thirdly, in order to address the label shift problem, we consider the balanced error risk. for this for domain transition. Okay. And lastly, given the distributions, we use the total variation to characterize the differences between the two domains. All right, so this is our the preliminaries. Okay, so now given this preliminaries, our theoretical results basically tell us, all right, if we have T domains, T source domains, and one target domains, and if we further assume that the embedding distribution phi satisfy a small feature conditional total variation difference on the latent space. Okay? In other words, the total variation of PZ given Y between any pairs of source domains is smaller than kappa. Okay? And also, if the total variation of the source domain and its closest, the total variation of the target domain and its closest source domain is smaller than sigma, epsilon. Okay? Then we can show that the balanced error rate in the task domain, okay, is upper bounded by this inequality. Okay, where this alpha TV is what we call the Duplication coefficients. Okay? It measures the total variation between any points in the representation space. Okay. All right. So now let's look closer at this upper bound. All right. So basically, in order to control the performance on a target domain, we have 4 terms to consider. The first one is just the error on the source domain. Okay. Straightforward, right? The second term basically is the distance of the conditional distributions over the source domains. Okay. This corresponding to the invariance regularization in the existing methods, right? So this term can be achieved by many existing methods. Okay. So this term is not a problem. Okay. We have a lot of methods to minimize this conditional distance. The third term is this epsilon, okay, which is the distance between the target domain and its closest source domain. Note that this term is unobservable because we never know what the target domain is. So in other words, it is uncontrollable. But it tells us like very like simple intuition, right? If the target domain is very different from the source domain, then domain generalization is hopeless, right? In order to do the domain generalization, we must assume that the target domain, even though we didn't see it, must be similar to at least one of the source domain in order to make the domain generalization successful, right? So this is an intuition. So there's nothing we can do here. The last term is a Duplication coefficient, okay? So basically it tells us, okay, even though we don't have the control on epsilon, but if we can make the alpha small, then domain generalization is still possible. Okay. So this theoretical analysis, this upper bound, reveals one thing that is missing in the literature, which is given by the alpha TV, right? The other 2 terms, you know, the error rate and also the kappa is well studied. Okay. The only thing missing here is the alpha TV. Okay. So now the question is, how can we control the Duplication coefficient? So in this work, we show that Duplication coefficient actually is related to the Lipschitz constant of the representation. In other words, if we can find a way that it efficiently control the Lipschitzness of representation, then we can achieve a low performance, lower pass rate in the target domain. Okay. All right. So this is the theoretical analysis. Now the question is, how can we achieve it? So in this work, we propose a very simple method. Okay. We design to regularize the Frobenius norm of the Jacobian matrix. In particular, what we did here is, given T south domain, we just sample T data points, one for each domain. And then we construct a new synthetic data points by the linear combination of them. Okay. And then we minimize the Frobenius norm of our loss with respect to this data points. By doing so, we can control the Lipschitzness of the representation. Okay. And note that this method actually is orthogonal to any existing domain alignment methods, right? Because domain alignment methods only consider the first two terms in our upper bound, so that we can just plug in this regularization term into any of them. So in this work, we studied 4 baselines. The first is ERM, just consider the first term, the source domain error. The second one is DNN, which consider the marginal alignments. The third one is CDNN, which consider align the PX given Y. Okay. And the last one is RIRM, which is the environment risk minimization. It considered to align the PY given X. Okay, basically the last two are two different conditional alignment approaches. We take these 4 methods, and then we add the our regularization term to control the Lipschitzness of the representation. We tested first on the color elements, right? So here the PS is the parameters to control the problem setup. And we can see that across all the baselines and all the experiment setup, our proposed method outperforms the baselines consistently and significantly. On average, it achieved around 4% to 6% improvement, which is very significant. Okay. For the second one, we tested on another data set, the PAX data set. Again, we have the similar observations. Across all the domains, we have a consistent improvement. Okay. All right. And lastly, we studied the influence of the regularization term. So here, lambda equal to 0 corresponding to no Lipschitz regularization. And we can see that as we impose the regularization, we get an improved performance. But at the same time, after some point, the performance get to a drop, which is also reasonable, because if we focus too much on smoothness, then we may lose the discriminative power, right? Okay, so this is the first piece of our work, which we studied the importance of regularizing the representation for domain generalization. So in our second work, we study another type of robustness, which is the robustness to noisy labels, also called learning with label noise. So label noise is also very common in real-world applications. For example, it is very expensive to get a medical image annotated because it is expensive to hire a doctor, an expert to do that. But what we can do is we can hire some students from medical school, right? Their annotation is cheaper, much cheaper, sometimes even free, right? But the problem with this is their labeling may not be perfect. There will be some noise in their labeling. Okay. Another example is we can also acquire labels from a crowd sensing platform, but still the label quality is not quite high. So now the question is, how can we learn from noisy labels? So it has been shown that the standard cross-entropy loss is not robust to label noise because of the memorization effect of deep learning, right? Deep learning is so powerful, so it can just memorize everything, no matter what the label is. So one common approach to address this issue is to design the noise robust loss function, okay, which prevent the memorization effect. But the side effect of this approach is it suffers from the underfitting problem, right? This is also kind of intuitive, right? There's a noise robust loss, kind of prevent the overfitting of a noisy label, okay? But at the same time, it may underfit the data with clean labels, okay? So in practice, what people usually do is just combine these two together, okay? So by doing so, we can kind of elevate the negative effects of both approaches, but at the same time, we also like those negative effects are also remain, right? Okay, so to address this issue, the motivation of our work is, what if we still use cross-entropy loss? Okay, because there's no underfitting problem. But we should avoid memorization effect, right? And we do so by learning a robust feature representation. So if the feature representation is robust to noise, then we can just use cross-entropy loss. Then we have the benefits of both work. Okay, so what is a robust feature representation? Okay, so in this work, we claim that a robust feature representation is a representation that minimizes the mutual information between the corrupted labels and the feature representations. Okay. So here is an example. So if we learn the images by using clean labels, we can see that the features we captured are quite consistent to each other, right? They are all focused on the cat faces, right? So in other words, the mutual information between the labels and the features are quite high. On the other hand, if the label is noisy, then the features captured can vary from image to image. For example, for this page, figure, the feature captured is the window bars, and for this figure, the feature captures are the floors and doors on the walls. Okay. So, in this sense, the mutual information between the labels and the extracted features is very small, right? Given the labels, we cannot tell what the features it may capture. Okay. All right. So how can we achieve this? Okay. So in this work, we investigate contrast learning and the effect of the clustering structure for learning with noisy labels. In particular, we first show that contrastive learning can maintain the information that is related to true labels, but at the same time also discard the information that is related to the corrupt labels. We also show that the representation learned by contrastive learning are robust to label noise. Okay. And lastly, we show that the representation learned by contrastive learning can also avoid underfitting. Okay. So now we have the benefits from the both work, right? Okay. Lastly, we given our theoretical analysis, we also propose a novel algorithm, and we show that by using our algorithm, the correct contrastive pair will dominate the learning process, which means the label noise will not affect the learning process a lot. All right. So inspired by SimSam, the contrast laws we studied in this work is given by equation 1. So here, xi and xj are 2 data points, and the q and the qi and the zi are the feature representations of the data points. Okay. And from this equation, we can see that if xi and xj from the same class, then the networks should push the data points together. Okay, the inner products of the feature representation should be very small. That should be very large. Okay. So this is the overall framework. And now we will study how this, why minimizing equation 1 will give us a robust representation to noisy labels. Okay, our first theoretical finding is by minimizing equation 1, actually we maximize the mutual information between z and x plus, where z is a feature representation of x, and x plus is another image from the same class. Okay. So intuitively, equation 1 encourages to put representations from the same class together and push those from different classes apart. Therefore, the estimate of z conditional on x plus is more accurate because the representations are more dependent on each other, right? Because of the cluster structure, basically, right? The data points from the same class cluster together, so the mutual information between them is increased. So this is what is the theory about. Okay, so we first build a connection between contrastive learning and mutual information. Okay, so now next we will show that why this mutual information maximization is important. Okay, so in order to do so, first we need to introduce a notion which we call epsilon gamma distribution. Okay, so here x and y are just a pair of data data point and its label, and the y tilde is the cropped label. Okay, and then we call a distribution epsilon gamma distribution if there exists gamma much larger than sigma, larger than 0, such that the following two inequality holds. Okay. So this two inequality actually is very straightforward and very intuitive. So first, equation 2 tells us if the two images x1, x and x plus from the same class, then if we already know an image x plus, there is a very limited extra information related to y by additionally knowing x. Okay. For example, if we already know that these two images are from the same class, then we can use, let's say, x1 and x2. Okay, then we can use x2 to predict the label. Right. At this time, by knowing x1 given x2 does not help us to a lot to predict the label, right? Because they are from the same class, they are very similar to each other, and there's no extra information. So this is a quite intuitive assumption. Okay. All right. Secondly, equation 3 tells us if the label is corrupted, then by knowing x plus, it is still hard to give us additional information to predict x tilde, right? We still need the information x to predict it. So in this sense, the mutual information between x and x tilde and the y tilde is still large given x plus. Okay, so this is just a very intuitive understanding of the clean labels and the corrupt labels. Okay. All right. So now, given this notion, we can build a connection between the mutual information and the robustness, or more precisely, the contrastive learning and the robustness. In particular, we have this following theorem. Okay. So here, the Z star is the representation that maximizes the mutual information between the representation and X class. All right. If we can learn such representation that maximize this mutual information, we can show that first, this Z star maintain the information that is related to a true label, Y here. All right. Because the mutual information here is upper bounded by X and Y, the mutual information of X and Y. More importantly, we can also show that the mutual information of Z star and Y tilde is upper bounded by this guy. Okay. In other words, if gamma is much larger than epsilon, we can show that the feature representation that maximize the mutual information between Z and X plus will discard the information related to the corrupt labels, because this guy is much less than this guy. Okay. And also note that we already built a connection between the mutual information and the contrastive learning. Okay. So in other words, by minimizing contrastive learning loss, we can get a representation that maintain the information related to true label, but at the same time also discard the information related to the corrupt labels. Okay. And since the corrupt the label information is discarded from Z star, then the memorization of the corrupt labels over Z star is diminished. So this is our theoretical result. And more precisely, we also have this following lemma showing that our methods for the contrastive learning loss actually can achieve the representation that is robust to corrupt labels. Okay, so first we define this E tilde, which is the event when the output of classifier is not the same as a corrupt label. Okay, so note that this is a corrupt label. Okay, so this guy, the expectation of E tilde should be as much as possible, right? Because large expectation implies the robustness to label noise. And also, if you look at the right-hand side term, this guy has nothing to do with the learning process, and also this guy, they're just the entropy of the classes. And then the last term mostly depends on the classifier built on the top of the representation. So the only thing matters for the representation is this guy. Okay, is the mutual information between Z and the Y tilde. Okay, and basically it tells this lemma implies that we should, if we can achieve a small mutual information between Z and Y tilde, then the representation will be more robust to label noise. Okay, putting all this together, it basically tells us by minimizing equation 1, small mutual information can be achieved as indicated by the upper bound in equation 5, right? This guy. Okay, and this small mutual information between Z star and Y tilde also tell us it will give us a robust representation to the label noise. Okay, so by doing so, we can build a connection between the contrastive learning and the robustness to label noise. Okay, the last piece of work is we can also show that our method can also avoid underfitting. In particular, we define this Rx. This is just the minimal risk we can achieve over the original input-output space. And this star is the minimal risk we can achieve over the representation space given by the contrast learning. And then we can show that this risk can be upper bounded by Rx plus a small term group zoom. Right. Okay. In other words, it means that a good classifier achieved on clean data can also be achieved over the representation Z star if we use the contrastive learning loss equation 1. Okay. So basically, it highlights the benefits of contrastive learning for learning with noise label. But there's still an important part missing, which is if we look back the equation 1, here, if we look at back equation 1, in order to minimize this objective function, we need to know the ground truth. It is a supervised contrastive learning method, so we need to know the ground truth, YA and YJ. But in practice, we don't have the ground truth because data set is noisy. All right, so how can we, if we just use the noise label, then we will get distorted performance. Okay. So how can we address this issue? We address this issue first coming up this following objective function, which is motivated by a phenomenon called early learning. So early learning basically says when we train a neural network on a noisy data set, the neural network will first feed the clean data and then the noisy data. So in other words, if we consider binary classification, then during the early learning stage, the clean data will give you the output either 0 or 1. And the noisy data will give you the output around 0.5. Right. So motivated by this phenomenon, the first thing coming to our mind is we can compute the inner product of the output between two images. So if the inner product is larger than a threshold, then they are probably first clean data. Secondly, from the same class, right? Otherwise, if the inner product is smaller than the threshold, then we can say they are either from different classes or their labels are noisy. Okay. However, there are still problems with this equation 6 because equation 6 only help representations during the early learning stage. After learning stage, the neural network start to memorize everything. It will keep updating the parameters in a way such that even though for some data points we have correct labels, the output will still goes to either 0 or 1s. Okay, this is what happens after the early learning step. Okay, and then we will have then we can see that this what we call wrong constructive pair will dominate the learning process. Okay. Why that happens? Because as I said, after early learning stage, all the outputs will approach either 0 or 1s, and in this case, all the pairs will be activated. All right. But on the other hand, if the data points are from two different classes, then we can show that with high likely, the inner product between the representation will be orthogonal to each other. And if they are from the same class, they will be aligned together. Okay. So in other words, after early learning stage, all the pairs, no matter correct or wrong, all the pairs will be activated according to equation 6. But the wrong pairs will dominate the learning process because of this term. Because they're orthogonal, so that the gradient of the loss function is much larger than the gradient of the loss of the correct pairs. So that's the issue. So in order to address this issue in this work, we propose another contrastive loss, which is given by this equation. And we can see that the L tilde, the contrastive loss we propose, still aim to learn similar representations, because the optimal solution of this contrastive loss and the previous one are the same. But at the same time, we can see that the gradient of this loss with respect to either correct or wrong pairs are roughly the same. Or more specifically, actually, the correct pair is still larger than the wrong pairs. Okay. So in this sense, the learning process will not be dominated by the wrong pairs after the early learning stage. Okay. So by doing so, we can still design, we can still use the contrastive loss to get the benefits as we analyze, even with the noisy labels. Okay. So overall, the objective function we propose is minimizing the cross entropy loss plus this L tilde, the contrastive loss. Okay. We just put these two laws together. So here is the results. We evaluate our methods on the benchmark CIFAR 10 by adding different level and different type of noise. And we can see that our method outperform those other robust laws significantly, especially when the noise level is high. Okay, when the noise level is 80 or 90, we can see that our methods has a large margin improvements over the baselines. Right. So this is the results on CIFAR 10. And this is the result on CIFAR 100. The same thing here. Okay, when the noise level is large, our improvement is significant. Okay. All right, so this is just a sensitivity analysis of hyperparameter. So here lambda is the parameter for controlling the regularization, the contrastive regularization, and this is the tau, the threshold. Okay. So this is just some sensitivity analysis. The next thing is the comparison of different regularization functions. Where the L prime is just the regularization function we proposed at the very beginning, which, as we said, will be dominant by the wrong pairs after the early learning stage. And the L tilde is the proposed regularization term we used in this work. And we can see that, again, it consistently outperformed, L tilde consistently outperformed the L prime. And especially when the noise level is high, okay, which actually consistent with our intuition, right? Because this term still, in this term, if you use this term, the wrong pair will dominate the learning process and will give us a very low accuracy. The last thing is, in this analysis, we use the SimSAM as the framework. But we can see that even though our analysis is based on SimSAM, but the high-level idea is quite general, and it can be plugged into to any contrast learning frameworks. So here we try another two contrast learning method, the SimClear, and also the BIOL here. And again, we get roughly the consistent results. So in both, basically it shows that our regularization term is quite general. It's not just applied to a specific contrast learning framework, but can be applied to most existing contrast learning methods or losses. Okay. All right, so this is the second piece of our work, which we studied robustness to label noise by investigating the contrastive learning. Okay, so the last piece of this talk is about fairness, which is a very recent work we under review for SML this year. So as I mentioned, another issue suffered by a machine learning algorithm is the unfairness, right? Because it may treat some group of a population in an unfavorable way due to the data distribution, selection bias, many reasons. So it is very important in many practical applications, such as resume screening, medical diagnosis, credit card scoring, or mortgage lendings. Okay, so algorithmic fairness aims to mitigate this issue of prediction bias by protect those sensitive features, okay, like genders, races, ages, and etc., etc. So fairness is a very very active learning area in the machine learning in recent years. So there are many rules for fairness, right? We are talking about fairness, but what is fairness, right? What is like criteria for fairness, right? There are many criteria for defining fairness, and here I list just 3 of them. The first one is independent rule, the second one is separation rule, and third one is a sufficient rule. Okay, so the first 2 rules are very popular and well studied in the literature. So this is not the focus of this work. So in our work, we study the sufficient rule, which is not quite well studied, but still very important in practice. So this equation is the definition of sufficient rule. Okay, basically, given the output of our algorithm y hat, the sufficient rule ensures that conditional excitation of the label, which is the y given y height, is invariant across different subgroups. Okay. And it has been shown that the ignore of sufficient rule can lead a significant bias in intelligent health. For example, in this science paper, the author showed that and the same predicted score, white hat equals to t, the black patients are considerably sicker than the white patients. So in this system, the output of is a let's say it's a health score. So a higher score means the situation is more serious, and we should give better or more treatment. Okay, and in this work, the authors show that actually, given the same predicted score for the black patient is more sicker than the white patient. Okay, so which is of course is unfair, right? Okay, so in this work we investigate this rule from the fair representation learning aspects. Okay. We shows that the sufficient rule can be achieved by learning an invariant feature representation. And secondly, we based on our analysis, we propose an implicit path alignment algorithm to learn fair representation, which address the prohibitive memory and the computational costs in the original bilevel objective. Okay. So first, how to achieve this sufficiency? Okay, so this is remember, this is the sufficiency we want to achieve. All right. So how can we achieve this? In this work, we actually started from this intuition, which is given a fixed representation function, if the optimal predictor that learned on the embedding space are invariant to different subgroups, then the corresponding representation is fair. Okay, this is the intuition. Okay, so what is how to formulate this this intuition? First, we need to define what is what is this invariant feature representation. Okay. So first, the H0 and H1 are the optimal classifier from two different subgroups. Okay, and we need they be the same. Okay, this is the definition of invariant feature representation, right? We need to learn a feature representation phi such that it achieves the minimal risk on both subgroups. At the same time, we also require that the optimal classifier H0 and H1 are the same, given the representation. So from the formulation, we can see that this is a bilevel objective problem, bilevel optimization problem, right? Because the optimal classifier or predictor depends on the feature representation. It is a function of the feature representation. Okay. At the same time, we also need learn such a feature representation such that the risk is small across both subgroups. This is a formulation. Next, we theoretically show that if we can learn this, we can solve this bilevel problem, then we will achieve the sufficient rule. Okay. This is what we show in this theorem. Of course, from the definition here, it is also easily shown that this problem is also consistent with this guy, the conditional distribution alignment problem. Okay, so this is consistent with the invariant risk minimization principle for domain generalization. In other words, the proposed framework can also be used for domain generalization problem, but here we only focus on the fairness problem. Okay. All right, so now we build the connection between sufficiency and the learning with invariant feature representation. The next question is, how can we solve this bilevel optimization problem? All right. Okay. So we all know that solving a bilevel representation, solving a bilevel optimization problem is very expensive. Okay. The standard gradient-based approach to solve this problem is called explicit path. And this approach needs to install old gradients. Okay, all the gradient steps during the optimization process, which is very expensive. Normally, it's in practice. It's impractical. Okay, so to address this issue, we propose what we call implicit path methods to solve this problem. Okay. So more specifically, we first studied Lagrangian relaxation. Okay, we replace this hard constraint with this additional regression term. the difference between the two predictors. Okay. So now we solve this problem. First, we solve this inner loop problem, which is kind of straightforward. We just solving this solve for H epsilon such that it is very close to optimal solution. Okay. Of course, in practice, we don't know the optimal solution, so we don't know what how to achieve this H epsilon. So what we do in practice, we just perform the gradient descent several times. Okay. But the good thing is, by using our methods, we don't need to store all the gradients of the path. We just need to store the last step, which is just the gradient of H epsilon, so which will address the computational issue. Okay. So in the inner step, in the inner loop, we solve for H1 and H0. So the main obstacle comes from outer loop. So in the outer loop, again, we compute the gradient of loss function with respect to the representation phi, and this is what we have. Okay. So the main issue with this gradient is this guy. This is the gradient of H with respect to phi. Okay. But the problem here is that H is, as I said, it is a function of phi. All right, it's a function of phi, and it is not an analytical function of phi. The way we get the H epsilon is just given the phi, we perform several gradient steps. That's it. So we don't know what we cannot write H in terms of phi. It is impossible. So we need some approximation to get this term. So what we do here is, first we know that H star, okay, instead of H epsilon, we studied H star. H star is the optimal solution. So we have that the gradient of the loss function with respect to H star is 0. Okay. And then we differentiate this with respect to phi. And then we can get this. We can get the analytical solution of H star with respect to phi. Okay. And since we know that H star and H epsilon are very close to each other, so we have the first approximation where we replace this H star with H epsilon. Okay. So this is our approximation of the gradient. Okay. All right. So now we have this our approximation, but still we have this issue. The issue here is this guy. So what is this guy? This is the Hessian of the loss function with respect to H, and we need to compute the inverse of the Hessian, okay, which is still very expensive. So instead of computing the inverse of Hessian, what we do is we solve the following quadratic programming problem, which is much more efficient. Of course, the cost here is it gives us another level of approximation, which is characterized by delta. Okay, so let's say the P0 is the optimal solution of this Hessian. Okay, of this guy. Okay, but here we replace this guy by solving the optimization function, and this is what we call the P delta. Okay, then the difference between them is characterized by delta. And now we get a final approximation, which is given by the gradient delta. Okay, so we have two levels of approximation. The first one is from replacing P star with P epsilon, and that second is from replacing the inverse of a Hessian with the quadratic programming. Okay, and by doing so, we can design very efficient algorithms to solve this bi-level optimization problem. Okay. Okay. So the next question is, what's the quality of this approximation. And we can see that this is answered by this theorem. And we can see that the gradient of our approximation and the real value of the gradient is upper bounded in terms of these three terms. Okay, so this epsilon and delta come from the two levels of approximation, and this kappa is from the fairness constraint. Okay? It requires H0 and H1 to be the same. So interesting, it reveals a trade-off, right, in the accurate gradient estimation and fairness and fair representation learning. So if we don't have this fair constraint, then we don't need to solve this bi-level optimization problem, and then we don't have such an approximation issue, right? So in this sense, we can get a better gradient estimation, but at the same time, we lose fairness. All right. Okay, so this is our proposed method. Okay, we propose this approximation approach to step size the computational issue of explicit approach for fair representation learning. Okay, so the next thing is empirical evaluation. But first, in order to evaluate the fairness of methods, we propose two metrics which we called sufficiency gap. Okay, so these two metrics, one for classification and one for regression. Basically, they measure the differences of the output, okay, given two subgroups. Okay. So here is the result on a two classification data set. And here we can see that, so the first columns are the accuracy. And the second column is the sufficient gap, okay? And we can see that our methods, if we compare it with other baselines, achieve relatively, maintain the accuracy, but at the same time, sufficiently minimize the sufficiency gap, right? So our sufficiency gap, is much smaller than the other baselines. And this is the trade-off between the accuracy and the sufficiency gap. Okay, so for accuracy, we want it as high as possible, and for a sufficiency, we want it as small as possible. So the optimal point will be the top left. Okay, so this will be something like the ROC curve. So we can see that our methods actually dominate the other baselines in different trade-off on both data sets. And this is a comparison of the computation time of implicit and explicit. And you can see that our method is quite scalable compared with the explicit learning methods. Okay, so the next thing is for the regression task. Again, here we compare the sufficiency gap and also the MSE. Okay? And we can see that our method maintain the accuracy, but at the same time get a much less sufficiency gap than any other baselines. The same here, but here since we use SME, so we want both quantities as less as possible. So the left corner bottom will be the optimum one. So again, our method dominates the other baselines. So this is a visualization of the sufficiency gap of our method. So this is our method, and this is another baseline algorithm. And we can see that our method is achieves much smaller sufficiency gap. All right, so this is the third piece of our work. So basically, in this talk, I introduced 3 pieces of our recent work on robustness and fairness. Okay, so for robustness, we highlight the benefits of representation regularization and the contrastive learning. And for fairness, we also show that the equivalence between the invariant feature representation and the fair machine learning. Okay. All right, so that's all for talk, and thank you for attending.